So we have like 2 hours about WASM and eWASM, and it's going to be an interactive session. And we're going to probably take a break at some point, maybe multiple. And we're going to have, how many? Like 8 people on the stage during these 2 hours. And you should be able to ask questions at any point of time. Okay. Yeah, so that's the agenda. I'm going to give a quick overview of what WASM and eWASM is. And then we're going to jump into some actual code examples. Next comes the client updates, because we do work on clients, and there's a lot of things to talk about what we did and how we did it in those clients. And after that part, we may take a break probably before the Python stuff, but it depends on how tired you guys get. And after those clients, we're going to get into the really deep technical discussion with EVMC and JITs, and maybe a lot of other things we may or may not have time for. Okay, I guess everybody should be familiar with these things. The EVM is kind of like an exotic machine, which is really wasteful, because most of the contracts don't really make use of this exoticness of 256-bit data types. And it also mixes a lot of high-level things with low-level things, which is probably a really bad idea. This is like my favorite one. Why do we have a SHA-3 opcode? That's like super high level. And it has a limited set of tooling around it, but that tooling is growing quite fast lately. So there are more languages targeting EVM and a lot of tools regarding EVM. But I think it still could be better. So who has heard about WASM here? Okay, maybe who hasn't heard about WASM? And who hasn't heard about eWASM? Oh, cool. So maybe we don't need to do a lot of introduction here. But it's designed by the W3C, but it's really open. Anybody can contribute. They have, I think, like twice a year, maybe 3 times a year, a panel where people can join and they can open new contributions. They can propose like major changes to the language, and that can be discussed. But apart from those in-person meetings, anybody can contribute on the GitHub design repo they have. It was finalized last year, but there are already, I guess, like 4 or 5 major proposals to extend it. And the extension is backwards compatible. So whatever new feature comes into WASM, the clients can make a decision whether they want to support it or not. It kind of looks like a regular machine. It's not as exotic as the EVM is. It is really a regular machine. The main goal is to efficiently translate it to a native machine. That was the main driving goal behind WASM. It doesn't have any such high-level, super high-level instructions as SHA-3. Instead, bytecode can import host functions, and that's the way to extend the language with more complex things. It's supported by all the major browsers, but there are also a lot of independent implementations outside of the browsers. And I guess this is the more important part, because it always comes up. With WASM, we're going to have a lot of support for different languages. And that's true. I've sorted these languages in terms of maturity of the tooling. And basically, we can start with anything supported by LLVM. So LLVM would be a compiler framework. And the most mature languages for WASM and LLVM is C and C++. But maybe you don't really want to use that for contracts. The next, which probably is at the same level of maturity, would be Rust. It doesn't, I think it does or doesn't use LLVM? I think it does, but it does now, but there was another project to make like a direct compilation from the Rust IR. So those 2 would be quite stable. But the next one is quite interesting. Who has heard of TypeScript here? Like a lot of people. So TypeScript is kind of like JavaScript with types. Kind of like a better JavaScript with types. And AssemblyScript is a compiler project which tries to compile TypeScript to WebAssembly. And as it turned out, they are a tiny team but they're really responsive. Funnily enough, there's also a Go compiler to WASM. We have tried it, but it generated, I think, 1.5 megabytes for a hello world. There are some tools to remove extra code from WASM bytecode which isn't referenced. There are multiple tools. One of them is called WASM GC. And running WASM GC on it would reduce it, I think, to 500K. But there was one part in it which couldn't be removed. It predefines a 500K memory segment with stuff in it. So maybe in the future Go would be supported, but right now it doesn't seem like a good target for contracts. There's also a Haskell compiler called DHC, but it's really minimal. It doesn't support a lot of features yet. It's driven by Definity, if you've heard about Definity. And the next one is Solidity, and there's another language next to it, Yule. Has anybody heard about Yule yet? 3 people. Have you heard about Julia? Have you heard about the Julia which isn't the big Julia? The small Julia. All right, so Yule/Julia is the intermediate language of Solidity. It was called Julia last year, but it conflicts with another language called Julia, and it has been renamed to Yule. So it's the proposed IR of Solidity. There's actually a proper parser and compiler from Yule to EVM 1.0 and EVM 1.5, and there's also support to compile Yule to WASM. But there's a big part which isn't there yet to compile Solidity to Yule. That being said, we do use Yule for some internal snippets in the compiler already. Have you heard about the new ABI encoder in Solidity? Do you know what the ABI encoder is in general? Okay, so basically the ABI is a way to interface with contracts. And Solidity has that implemented in a really bad C++ code to generate this ABI encoder which is injected in each of the contracts. That is one of the big parts of what should be in the intermediate language. And we actually have already rewritten using Yule. And that is the new ABI encoder. It's called ABI encoder v2. It can be enabled in the language using an experimental pragma. And we would like to basically we have no idea yet how to get people to test it. Because it's marked as an experimental feature. We would like to release it. People depend on it because they want to use structures and high-level data types that's only supported by this ABI decoder. But somehow, if we get people to test it, we can enable it, and that's already going to use this intermediate language. And that probably will enable us to move a lot more of the compiler to the intermediate language, and as a result, it should be able to compile Solidity to WASM. And regarding Viper, I'm actually quite lucky that I'm talking after Jacques. Viper currently compiles to LLL. And there's a prototype LLL to Yule compiler. But that still wouldn't really help you to make use of smaller data types, because LLL right now is really 256-bit dependent. So I guess Viper will have multiple options to target WASM, but one of them would be to target Yule as an intermediate language, and then make use of Yule to compile to WebAssembly. And lastly, there is a lot of work going on in the K framework to support WASM and to support eWASM. So that's a lot of languages already, and probably I missed a ton of other languages because they're popping up every day. Yeah, all name, yeah. Yeah, there was, I'm kind of uneducated, but there was somebody yesterday who said he's the creator. Hey, nice to meet you. Yeah, I actually, Jacek had like a demo to compile it to WebAssembly directly somehow. Yep. So, yeah, name should be supported as well. There's going to be a challenge listed later to create eWASM contracts. So I'm inviting you, Jacek, to write it in them. It could be a status bounty. All right, so that's about WASM and languages. Any questions so far? Okay, let's move on to eWASM. So eWASM was really designed to be 100% EVM compatible. And what it means, it has all these host functions, all these features exposed to eWASM contracts, which are made available to EVM as higher level instructions. So it has all the same kind of calls, it has all the same kind of storage access, it has all the same kind of state access. And that means it's possible to write eWASM contracts which can 100% interact with EVM contracts. But it has been designed to be extensible. So we can remove some of those, and we can add new ones. And that's really important because even though it started out as a 100% compatibility with EVM, with the goal to launch it on the main chain, but if we decide to not launch it on the main chain, maybe we can improve some of these and remove some of the old methods which don't make any sense anymore. Okay, so what's the current state? The API is stable, this EVM compatible API. And we have quite a few ways to support clients. So the native one is in CPP Ethereum, and there's going to be a more extensive talk after this on this topic. There's also native support in Go Ethereum. Again, there's going to be a talk about that. And there's in progress work with PyEVM/Trinity. Again, a talk about that later. But there's also universal way to support one of these implementations in any client by implementing a Slim API. And we're going to expand on that later as well. Okay, regarding languages, we do have a native framework in Rust, with an example coming. A native framework in AssemblyScript, and in C. We have written a couple of precompiles in C and Rust, which we're going to share today. But there's some other system contracts which still have to be written. So any help is welcome. Maybe it can be written in NIM. The other things we are currently focusing on is more research-based. We're researching on vulnerabilities. One of them is regarding JITs. A lot of questions have been raised around JITs, and we try to address all of those questions. There's going to be a talk about this today. And we're trying to help out Solidity and Viper to support eWASM. Okay, so how to participate? We have a bi-weekly community call, which is open to anyone. We have been running that, I think, for the last 2 months. And there has been a lot of people joining, usually in the range of 10 to 30 people each call. Anybody can join, they can ask any kind of questions. It's fully free. There's a page to put agenda points, but nobody ever does that. But it works out. But now we're going to start a developer call as well to make decisions. So every 2 weeks. And the next one is the 5th of July, which is Thursday. Whatever, it's next week. That is free to participate as well. We do have agenda points there. And those agenda points we would like to make decisions on. Maybe we can make decisions on the first call. Probably not. But I invite everyone to join. Please read the spec and comment. Because it's kind of stable, so it can be discussed, and it's stable to be changed. And please write a contract, so there's going to be a challenge posted here. Okay, so probably everybody knows about these URLs. Just please join the Gitter channel, and you're going to be updated about all of these progress we're making. Okay, so one actual real contract is in Rust. I mean, there's not too much to explain about it. As you see, there's a call data size and a call data copy method, as you would expect from EVM compatibility. There's a way to consume gas, which would be inserted during like a metering process, but because this is a precompile, we do it manually. This is like the magical gas calculation we do in precompiles. And lastly, with the finished data, we are just returning the calculated hash. So whoever has implemented the SHA-256 precompile probably has done the very same things already. If we get to use eWASM, you may not need to do it again. You could just compile this snippet and use it. Any questions on the snippet? Yeah?
you were actually deploying this to WASM, you wouldn't need the consume gas call?
Depends. So if we keep this magical gas calculation, the precompilers have, because the precompilers have like a random number assigned to them how much they cost, right? And if we just meter this contract how we would meter anything else in eWASM, then probably it would come up with a different cost. If you're happy to accept that, then you don't need that line.
Right, I guess I meant if it were deployed as a contract rather than as a precompile.
Oh yeah, of course. All right then. So this is the challenge I was talking about. Of course, it's a token writing challenge. And we termed it WRC20, where the W stands for WebAssembly. Where can I open this? Yeah. How do I make this like full screen? Is it readable? Okay, so that's just, basically it has two functions: to query the balance and to transfer tokens. And there's an initial address which holds all the balances. There's a private key for it. It would be kind of compatible with how the ABI works currently on the network, except with one change. We've decided to make it 64-bit based because there's no point to have people implement big number libraries in any of these languages in order to write a token contract. And if we move on to maybe WASM, maybe we don't even need to use a 256-bit ABI. But it would be pretty much similar how you would write anything currently as a contract. It uses the same kind of hashing for the ABI selectors and same kind of data encoding, except it's not 256-bit. This is a pseudocode of the data flow. And yeah, I invite everybody to write a contract in the language of choice. And they can actually test whether they have implemented the contract properly. These are the 4 test cases you should pass, and then you're fully audited. Okay, and now we should hand over to an actual implementation and maybe see what were the challenges faced during writing that contract, and maybe some other learnings. So Casey, if you want to join, because it was written by Casey.
Hi. Yeah, I don't know Rust. I started out, my first experience with Rust was using parodies, CK-snark precompile stuff that was added in Byzantium. So I took parodies library for that and compiled it to asm.js to be used with Ethereum JS VM. So yeah, I learned just enough Rust to do that, which was basically banging on the keyboard until it compiled. So building on that stuff here, these externs are the EEI methods. Sorry? So we're only using 5 of them in this example. It's not fully working either. But I guess what I want to show is when it compiles to the WASM code. So one of the nice things about the Rust WebAssembly toolchain is it does generate nice small binaries. So this is the assembly, so you can see it gets converted into these import statements. And then we do have to change the env to Ethereum. There's no option to do that in the Rust WebAssembly compiler, so we have to do that as a post-processing step. Then here you'll find those calls to the EEI methods, or eWASM methods. Yeah, and
it looks tiny.
I mean, it is a lot of assembly code, but file size wise, it's yeah. Paul did a handwritten version. But I'm going to pass it on to the next one, which is the assembly script version.
Hey guys, I'm Lane, and I don't know assembly script either. Also, bear with me because I didn't sleep on my flight, and I'm like super jet lagged. So I'll just keep this brief. So look, I think like languages like Rust and Go, C and C++ are great, but speaking as someone who has a background as a full stack web developer, and also kind of like looking to the future of Ethereum and trying to make it into a platform that I think will appeal to masses of developers, I think something that looks and feels and tastes a little bit like JavaScript would be kind of a smart route to go. And I think that this assembly script, because it's sort of a member of the JavaScript family, accomplishes that better than languages like Rust and Go for people who already know things like JavaScript and don't want to like learn a completely new kind of language stack. So just briefly on assembly script. So assembly script is a restricted subset of TypeScript, which, as Alex explained, is a superset of JavaScript. It basically just adds strict typing to JavaScript. Assembly script has some restrictions. Assembly script, strictly speaking, is not a language itself. It's, as I said, sort of just this restricted subset of TypeScript. It has some restrictions, like TypeScript allows, I think it's called an any type, which would, I guess, have some sort of type inference happening because TypeScript is still running inside the JavaScript runtime. Assembly script is not, needless to say, right? This is compiling directly to WASM, so it sort of removes some of the flexibility of TypeScript. And yeah, as I said, I never really used assembly script before, and this took me, let's say, an hour to get it working. So I think Casey said it took you 2 hours to do it in Rust. So that's pretty exciting. So just kind of looking at what this code looks like, it should look a little bit like JavaScript. The one thing that like really stands out is, to me at least, is that we're still doing some memory allocation and we're still working with pointers here. So what you're looking at here is native assembly script. I didn't have too much trouble with this because we've been writing WAST, which is the text version of WebAssembly, by hand for months. And so this is sort of like, after slogging through the sort of dense, deep jungle, which is like WAST, it's like we're now at 1 level or 2 levels of abstraction higher, which is really, really nice. So basically my goal here is while we have to do this sort of memory allocation and we have to work with pointers, and the reason for that is that these calls, so for example, this call data copy here, right? This is a call directly into the host function in this case, right? So call data copy is obviously, is reading into this pointer here a certain number of bytes from the call data that was passed into this function. Wait, this is still a little bit too low level because we have pointers and because we have memory allocation and loading and storing memory directly. So I guess my goal here, something that both Alex and I have been working on, is to move yet 1 level higher in the abstraction here and wrap these functions in something that sort of handles the memory for us. So we don't have to, so the developer doesn't have to think in terms of pointers and number of bytes. It would just sort of figure out the length of certain types automatically. And I guess what I'm getting at here is I would like contracts written in assembly script to look and feel a bit more like Viper or Solidity than WASM. And so we're kind of in this weird in-between place right now. Yeah, so this should look familiar if you saw the prompt that Casey shared a moment ago and Alex shared. This is just a very, very bare bones ledger implementation of this WRC20 challenge, do balance, do transfer. And I think, Casey, do we have the WASP code is here. Wow, that's really tiny. So again, this looks very similar to what Casey shared a moment ago, and it should, obviously, because they're 2 implementations of the same thing. We have these host functions being imported at the top here. And I think, Alex, you also mentioned this. We noticed that the assembly script team, which is really small, are also sort of very, very responsive and very friendly. And like we had this issue, which Casey also mentioned a moment ago, that by default, these imports are attached to this namespace called env, and there was no way to sort of fix that in the tool chain. So what I've been doing is this really obnoxious manual process where I compile the assembly script to WASM, and then I convert the WASM to WASP, and I go in with a text editor and change env to Ethereum, et cetera, et cetera. So within literally 8 hours or 10 hours of sort of us having a GitHub issue open about this, the assembly script team jumped in and added a feature and they cut a new release of assembly script that now this is no longer an issue. So this is actually not the latest code. So yeah, I'll pass the mic back, but just wanted to add, I'm personally very, very excited about assembly script. I think that it's going to be a really awesome tool chain for all sorts of contract development. I'm even thinking about doing some of the like precompiles and stuff in assembly script. So excited to keep people in the loop and share more updates about that soon.
Thank you, Lane. If the Wi-Fi works, we could also show one thing. Let's just give it one quick try. Okay, we can show it later after the break. So we should, okay, one thing though. So anybody who wants to take part of this challenge in whatever language, even if you want to write it in Rust again or assembly script, you're welcome to do it. This is the bit.ly. Is that readable? K2KIJQAD. Well, or you go to gist and my username, you're going to find this. But yeah, please try to do that. And now I think everybody's still like awake, right? We can go to an actual client implementation. Okay, let's do that. So where are you, Jake? Come onto the stage, please. So we're going to talk about CPP Ethereum. And you have a question?
Yeah.
Quickly.
In terms of size of the final bytes, right? That's the WASP, right? That's like some type of intermediate.
In terms of the final byte size, how much bigger is it than the current bytecode we generate?
Elaine, do you remember how big it was?
Yeah, so one of the really nice things about assembly script is that it produces really tiny binaries. There isn't really like a standard library or anything for assembly script. It's very new. Sorry. Yeah, the binary that it produces is, that assembly script produces is really small. I think it's about 420 lines of WASP. Bytes, 400, 500 bytes, something like that. It's really tiny. It's a lot smaller than like the Rust one, for example. Can you go back to that like 5th browser tab there, Aksik?
But I can give you the figure for the SHA-256. That's in the range of like 8K compiled.
So this is only 247 lines of WASP, which is tiny. And the Rust one was like more than 1,000, I think.
But that's before the GC stuff, I think.
No, it's after.
After the GC, okay, that's bad. Okay, so let's, where was it? Let's invite Jake onto the stage regarding one of the client implementations. And of course you can ask him questions, I guess all over.
Hello everyone, I'm Jake, and well, I'm going to be giving a brief overview of Hera, which is the primary VM implementation of eWASM. Is this mic working? Hello? Yeah. Alright. So here's a quick stack diagram of how we use Hera with CPP Ethereum. Well, as you can see, CPP Ethereum connects to Hera through the EVMC interface, which is an API that the client used to connect to the execution layer. And Hera communicates with the executing WASM module through the host function interface, or EI imports, and a VM abstraction layer, which makes it easier to switch out WASM engine in the future. So Hera is written in C++, which makes it easy to integrate with the EVMC API and use it with CPP Ethereum, either statically linked or as a shared library. And, well, yeah, it communicates through the EVMC API, unlike a traditional EVM implementation, which would instead communicate through direct library calls. So Hera's job is essentially to validate and execute WebAssembly contracts as well. Well, it does this using the binary interpreter at the moment, but that can easily be changed with the aforementioned abstraction layer. And the other function it has is to expose the host function interface to the executing WASM module. Now, so a WebAssembly module has the ability to import and export functions and global data, and so in place of high-level instructions in the EVM, we use a set of standardized imported functions that allow the executing WASM module to access the functionality of the client. And so here we'll go into a more in-depth description of what the Ethereum host function interface is. So it stands for the Ethereum Environment Interface, although we're currently working on a revamp of what that actually means at the moment. So as I said earlier, it allows the eWASM contract to access client functionality like state querying and data copying and calls in the form of a clearly defined API that's exposed to every eWASM contract. So in EVM1, we would have this giant problem of mixing abstraction layers that would result in performance problems and generally poor design. And so it consists of two components. The main one is the host functions that, as I said, provides the state querying and other functionality to the eWASM contract. And then we also have a set of debugging functions that are used in a testing context. So here is essentially the glue code between the WASM engine and CPP Ethereum, which, to which it connects to through the EEI and EVMC respectively. So Hera recently has been upgraded to have a VM abstraction layer, which allows us to explore the prospect of using different WASM engines to execute eWASM contracts. So at the moment, Hera uses the binarian interpreter, which is essentially a toolkit for WASM that, well, has a couple functions, including compiling WASD and interpreting WASM bytecode. So the next stages of WASM engines will probably be Wabbit and Wabm, which are currently a work in progress. So Wabbit is another C++ interpreter, and it's a good alternative, and it's also gives us the opportunity of differential fuzzing, so we can test for discrepancies between the behavior of different execution engines. Now, the more interesting one is Wabm, which is a standalone LLVM-based JIT compiler, and obviously that would provide to us some major performance benefits that allow us to take full advantage of WebAssembly. But there's also a couple concerns about vulnerabilities in JITs that could cause some denial of service attacks on the network. So to test these and compare their performance, we're also working on a benchmarking module for Hera that will allow us to get better data on which WASM execution engines work best, and also potentially for what types of bytecode. And so now I'll pass it off to Guillaume, who has an overview about WAG.
Thank you. All right. Can you guys hear me? Oh, yeah. Jake has already explained basically what our work defining the interfaces was going to be. So my focus is going to be on explaining, like, maybe what I did with the Go implementation, and the lessons, the issues I encountered. So we have this pre-existing VM existing in Go that's called the Wagon. It's an independent VM, so it's been developed by three main developers. I think one of them works for CERN and one of them works for Google. And their goal was indeed to get Go contracts to compile, Go code to compile to WASM, and then execute it on a Go virtual machine. So that has caused some problems because, they were not interested in extra features. So I had to negotiate with them. I'm still negotiating for some features. But it was missing, for example, host functions. So you could not call from WASM. You could not call functions in Go. yeah, it doesn't currently have a debugger, so I have a PR that I'm going to release probably next week. So I expect some infighting again. But this being said, I'm trolling a bit, but at the same time, the advantage of Go is that you can easily take a different project and integrate into your tree. So when it came to interface with that, that was actually pretty easy. So the current status, I have an initial PR if you want to go and get some inspiration, like if you're looking into porting that, like porting eWASM to bringing NIM to eWASM. I have an example in Go, and at the moment we support the EEI, and the next step is of course to optimize. I have some talk about this in a bit, but yes, like currently it's about running it on the test net, making sure that everything works, and hopefully we can get Geth into the other list of supported implementations. So the lessons I've had that I wanted to share, it's basically that people, especially in Go, will try to impose the language philosophy on WASM. So Go, as you might know, is extremely opinionated, let's say. So everything has to be done the way Google wants you to do it. For example, in all the negotiations I had, there's an interface. Host functions need to access the VM memory, otherwise they're completely useless. Yes, people wanted to. Go is a garbage collected language, so you have this nice function called make. You call make, and you get your memory, and you don't think about allocation and all those things. So those people wanted to have the same thing from host functions, being able to call make and be able to allocate memory inside the WASM memory, which of course meant like you had to rewrite the garbage collector. That would be like the third, because there's the one in the WASM Go runtime, there's the one in Go itself, and then there would be a third one. So that's a bit overkill. So there's a bit of a philosophical debate at the moment. And so yeah, that would be my first warning. Make sure that what you bring when you implement WASM to your own language, make sure that you don't bring too many baggage with it. What I found was reflection and polymorphism really helped. I mean, yes, so for example, at the moment we have 3 potential VMs to integrate into Geth. There's the Wagon, there's the EVMC, and there's the Python, more of which you will hear later. Yeah, those things mean like hacking a lot. So thanks God, Go has some fairly nice interface type. You can just switch that at runtime. It's pretty nice. And yeah, I think I'm missing. Yes, exactly. When you're not sure, well, the EVM already has all the real issues solved for you. So just make sure you understand the EVM before you get started. And the last thing, like the last warning, is the calling other contracts is actually a bit tricky. At least the way it's implemented currently in Wagon is extremely inefficient. So that's what I need to work on next. It's basically you have a VM. You need to instantiate a new VM that is extremely heavy. Call, let it execute, and then recover the context. So that is the not so nice element about this. And that's pretty much it for me. If you want to discuss the details of the PR, I'm around. And the next, I don't know, are we having a break or are we passing on to?
Well, I guess, are there any questions?
Yeah, of course, there's questions.
Any questions for Wagon or Hera?
Hopefully. Stay here.
So it's not a question about Wagon, it's a general question about eWASM. It's something that occurred to me when, so if I'm writing a contract or something else in C++ or in Rust, or even in Go, there are standard libraries, right? For example, nobody these days writes the hash maps anymore. They just use standard libraries or arrays. So, and as I understand, like, how do they look like in eWASM? Would you be able to use the standard libraries for STD map, and how do they look like in the eWASM code? So would I be able to do that, or just have to rewrite my hash map in the eWASM myself using this host function calls? And that leads me to another thing, which is not as a question, but maybe as the idea to look into. So in hindsight, I think when Ethereum decided that this contract storage will look like a mapping where you can just specify the address and you get that, unfortunately led to some of the unwanted behavior. For example, that people treat the contract storage as if there was some sort of hash map, and that's why, for example, the arrays are more complex than mappings in Solidity or in Viper. And so I would, in hindsight, I would say that the contract storage should have been implemented as a memory, as like a contiguous storage would be. And this is where you would actually be able to use standard libraries and stuff like this. So maybe before you solidify the API, maybe there's a chance to change this architecture in Ethereum and not simply follow what EVM does, because it might not do things really well in the hindsight.
Yeah, I mean, at least I can get started. So the first point is, yes, of course you can use the library. So it's basically just outputting to a different binary format. So if you just link everything statically, you can get most of your functions. Namely, for example, the Go runtime. I think Alex was mentioning before that if you try to compile smart contracts in Go, they are absolutely huge, and that's because the whole runtime, all the libraries, like Go tends to grab everything and make fat binaries. So that's why you also get fat contracts. And you have the whole runtime, you have the GC, you have everything. So you will not have to rewrite every single piece of your stack. Regarding the design, I mean, I don't think I'm the person to take the decision, but why not? I mean, maybe someone else wants to address this more specifically. But as far as I'm concerned, yes, we could. I mean, at the moment, we have this EEI that definitely writes the contracts into. Writes into the store like this way. But if you want to use memory, I guess that can be considered.
Yeah. Sorry, before, because there were like, how many? Like 6 different questions here. Just regarding back for the first one, regarding whether you can use standard libraries. You can use whatever. The output may be like quite big. And when we have metering with its own rules, that probably will spark reasons to optimize your compiler or your code to certain ways. So you may want to have like a hash map implementation which is gas optimized. And second to that, there are a couple of proposals in this host functions to have a couple of basic things exposed which can be used by the contracts. And it's also possible to expose like libraries. Are you familiar with like how Solidity libraries work? So not that way, in a better way. You could with WASM dynamic link with other WASM contracts. So there could be standard libraries based on the chain, and you wouldn't need to compile those things into your contract. And I guess the second question was more related to the stableness of the API. So where we stand right now is we have this stable API to start with, and we have like 2 clients fully working. So it's like a perfect time to actually have a discussion and think about how we would like to change the API and how we would like to change Ethereum. So that's where we would like to have a lot of discussion with the research team, how this could be used for sharding, or even if we would like to introduce in the main chain. Everybody is free to make proposals, how maybe change the storage or anything else, because probably there's a lot to be improved on Ethereum there. And those are like great questions. Thank you.
Actually, to answer for
coming back to that specific comment about more and more things going into WASM sort of libraries, how does that affect the trust model? I mean, suddenly there's contracts, they live on chain, right? But if we start dynamically linking in stuff from WASM implementations, more and more goes into there, how does that affect the ability to know what you're running?
Yeah, so the dynamic linking, one of the proposals would mean, okay, let's just open this thing up. Maybe they're at the top. Okay, this one was shorter. So we have this, this big blob of imports. And in WASM, imports have a namespace, which is the env here, and have the function name. And by default, all the compilers use this env as a default namespace. So whenever you import something, it's going to use this namespace. Whenever you export something, it's going to use this namespace. Some compilers have like native support to have like an annotation for the namespace. So this assembly script compiler has a way to do that right now. And if the internet would work, I could show it. Rust has a plan to support it, but it's not in the language yet. And there's an attribute in C++ to support it, but I don't think it's supported by CLang yet. And the reason I mentioned this, dynamic linking, one of the proposals means that instead of like the Ethereum namespace, there could be a contract address here. And that's the address we load the code from. And that code could, so there are not only like import statements, there could be export statements. So here with the func, we declare this function, and we could have a statement that we export this function under the name whatever. And if that blob is deployed on the chain at a specific address, we could import that method from that specific address. So that's one of the ways to do dynamic linking. Now the problem here is, I guess, if you like self-destruct the contract somehow, or somebody changes that contract. But I think this is kind of, at least at the moment, out of scope of eWASM to make a decision on that. You know, that's like a governance. Who governs those contracts you're going to use. But I might be wrong. So if I would be glad if you could open like a topic on the design repo and discuss this in more depth. Does that answer it in any way?
A little bit, but like the real question is here: how much weight do we put on the chain? Like how much of the code goes into the chain, and how much goes into the VM and support functions that are supposedly generic amongst implementations? Say, I don't know, Ketsak hash or whatever it might be, right? That ostensibly you could put that on the chain and then have a verified implementation that's safe.
Yeah, we actually have this other notion, system contracts. So the precompiles would fall under the system contracts. And what we could do is provide this single WASM implementation of the precompiles and a single like library implementation, which would then be part of the state in the sense the code hash would be there, but it doesn't need to be deployed on the actual state, but the clients, each of the clients would have to have it. So it could be done that way, or you could choose to have it in the actual state. Any more questions on Wagon or Hera? Okay, then should we take a break now, or are you interested in the Python stuff, which should be another 10 minutes, and then after the Python we have this big discussion of the universal API and the JITs and all the fancy things. Python or break? Python. Okay, let's invite Paul. Oh, testing.
Hello, so my name is Paul. I am trained in mathematics. I am working to write WebAssembly as an Ethereum Foundation grant. That's what you see on the left side. On the right side, you see the WebAssembly spec document. W3C is sort of putting together this document, and I've been reading it. I thought I would implement it in 2 weeks. It took me 2 months, actually. And so I just implemented it word for word. You can see 4.5.5, 4.5.5, invocation. There's steps 1, 2, 3. There's steps 1, 2, 3. So I don't think I did anything controversial, and I think that. But what I learned was when I was writing this, there's a lot of subtleties in this spec. There's a lot of structure, and if you think that you're just going to implement it just like the EVM, just do the opcodes, it's going to be difficult because there's a lot of structure for importing and exporting functions, for doing all of these indirect things called indirect calls that model function pointers. Maybe I'll scroll down, but there are opcodes actually in WebAssembly. So here's sort of a lists of opcodes, and I have some lists of opcodes as well. But this is some 4,000 lines of code that it took me. But it's nice to have sort of a translation from the spec to Python, so we own it, we control it, we can do whatever we want with it, we can test new features to expand the language, to contract it, to suit our needs. And we're talking with PyEVM people. They might be interested in using a full native Python toolchain. And they would use PyWebAssembly as their execution engine. Their concerns include tracing, very important to be able to trace things. I also found out that the people at TrueBit might be interested in tracing as well and outputting the state at each step. So right now I'm working on tracing things and logging. For example, you want to debug your code that you executed. There are no good tool chains to debug your WebAssembly code that I know of. And it would be nice if we can step through, opcode to opcode and see how the stack changes, see how the memory changes, these kinds of things. So this is ongoing work right now for me. And maybe I'll mention, the WebAssembly spec is still sort of, there are still some typos and things. I submitted some changes to this 150-page spec document. I have more changes coming because there are some small errors, nothing major. And something very interesting, I think we're going to have a break. I guess we'll open for questions before break, but after break, before I open to questions, there's something interesting about implementing things. And Pavel will talk about some sort of, when you have a client, you want to isolate the VM completely, perhaps, from the rest of the client. So we'll hear about that after the break. But right now, I'll open for questions.
Curious, what was the scope and the goals of the grant? Just to do a direct Python translation of the spec?
No, there was nothing written about direct translation. The goal was to implement it and pass some spec tests. I'm currently passing all spec tests that are relevant to us. I'm still refactoring some things, but the things that are relevant to us, all the spec tests, everything is done, ready to be used. It's not aesthetically, some things need to be sort of refactored in terms of aesthetics and also to be more usable. Right now it's a 4,000 line monolith, what I wrote. Did I answer your question?
Yeah. Have you done any performance analysis?
Okay, something very important. So I'm interpreting, so there's like interpreter that's being interpreted. So I'm interpreting WebAssembly and Python is being interpreted. So there's some sort of archaeological, layers of interpreting that are going on. So it's slow. It's not, maybe it won't be used in production. I compiled some Fibonacci code to C, which is like milliseconds, and this took maybe seconds to execute. So there's a big push, and this is a theme of what we're thinking about, is we would like to use things like JITs or ahead-of-time compilers to get speed, because interpreting might not be fast enough for production. But for studying, for experiments, for prototypes, I think this is great. interpreting is just fine.
Thank you. Thanks, Paul. So having done this implementation once now, if you were to start over and do it again, like what are the couple things you might do differently?
I made some bad design decisions. I think it's a good idea to conform to the spec. It's written, it's a lot of structure, it's a lot of, they do things for a reason. And you're implementing it, you say, why are they doing this? I'll just do it my way. And then 20 or 40 pages later in the spec, aha, that's why they did it this way. So now I have to go back and refactor everything. And this happened several times to me, so I got my butt kicked and I had to go back and conform with the spec documents.
Thanks. Can you talk a little bit more about tracing? Like how is that going to work and how might it be integrated? I mean, if this is better to be saved for after the break and Pavel, then that's fine as well. But how would it be integrated into the clients?
On the granularity of opcodes, I think in clients, okay, so what are we tracing? There's two things to trace. There's these calls into the Ethereum, you know, give me some storage state, set this storage state, and then there's at the granularity of these opcodes, of these WebAssembly opcodes. And I think if these two things are separate, if we keep PyWebAssembly as a separate entity from this sort of interface glue code to the client, we would like to trace both actually, and both do things, and so we would have to sort of pass control of what's tracing, and we would have to sort of integrate everything. So there's these kinds of thoughts, but I think the tracing would happen at the granularity of WebAssembly opcodes, and WebAssembly is stack-based, so we would print out perhaps the stack or print out chunks of the memory. Maybe there's some control structure that we're in right now, or some nesting of functions that we're in right now that would be relevant. Of course, TrueBit's demands might be different from PyEVM's demands, so it'd be nice to have something that's flexible and generic enough so you can set some parameters of exactly what you like.
There's like a standard EVM trace format that we've been seeing a lot of in like CPP Ethereum, so it might be interesting to think about what that would look like for eWASM because it's a different type of instruction set.
Yeah.
So the primary kind of user of this particular implementation would be a researcher or somebody just studying particular constructs and so on, right? Compared to, say, CPP Ethereum or Go Ethereum.
Yes. Yes, I think that this was a good tool for studying and sort of prototyping, yes. At first, maybe it might be usable on the whatever, live, a full node. But eventually, I think it's not going to be able to keep up on precompiles if we're talking about, milliseconds or macroseconds versus full seconds or tens of seconds. It's not going to be able to keep up. So yes, it's for research for now. There's another question.
Actually, I wanted to ask a question.
Okay.
Sorry, just the mic is here. Thank you for all that work. It looks enormous. And having done that and now it passes the tests, do you see opportunities to modularize this a bit and break it up? And yes. Are you looking for contributors for the project?
Okay, so there's two questions. The modularize, yes. At the granularity of chapters, this WebAssembly spec has like 7 chapters, so I'll modularize it at that granularity. I want to keep as much, keep it as close to the spec. The spec is sort of functional programmers writing in OCaml, and I think that I want to keep it as close to their sort of model of programming as possible. So I don't know if objects, they're not using objects. So I don't know if it's a good idea to force, classes onto this. Maybe, I don't know. And am I looking for contributors? Sure, but this is 2 months for me to get to the state where I'm in now. So there is going to be some growing pains if you want to make an effort. I'll be happy, but don't feel obligated. Hi.
Hi. Could you go through how to actually use this library?
Yes. So in the spec document, they define something called the standard embedding, which is a list of maybe 30 functions that if you provide the user with these functions, they can do whatever they want. they don't have to go into all of these other, the rest of the spec. So I'm actually using, among these 30 functions are init store, decode module, WASM, everything you see, WASM, get export. So if you look at it's in the appendix, chapter 7.1 of the spec, and you read through those functions, you can, but that's precisely what I did here. So I have a module called Fibonacci.wasm, and I go through this sort of stuff. It's a little bit complicated, but I'm just following, I'm not doing anything controversial, I'm just following the spec. Maybe I can sort of wrap this up into my own function that says, do all of this at once so that the end user doesn't have to think about these things. I think that's a great idea, but I also want to maintain the API that they sort of recommend. There's a question here, or?
So actually I have two questions. One is, does it have any dependencies, like Python packages you're using to implement that?
Only in the Python standard. No external third-party dependencies as of right now.
So because of that, maybe it would be interesting to check how some JIT-powered Python implementations would behave with that.
Yes.
Because I guess it would be quite easy to use PyPy or Cython to actually speed up execution a bit, and then we can compare performance.
Yes, with Cython I would have to annotate types, I think, manually for everything.
I'm not really familiar with that one.
But with PyPy, yeah, perhaps, and there might be some JIT things. So yes, I can play around. I haven't done this yet. I've been more interested in getting all the spec tests passing. But yeah, I think, yes, very good point. I definitely want to study the whole Python environment and see if there's any cool tools I can use with this.
Good opportunity for contributors.
He said good opportunity for contributors then. Yes.
My name is Pavel, and I work on some of C++ projects related to Ethereum. And we're going to have, we're going away a bit from WebAssembly and eWASM. And what I want to present here is mostly what this EVMC that has been mentioned so far sometimes, what is it and how do we use it at the moment. So starting from Ethereum virtual machine, it's this piece of software we have in every client that actually executes the smart contracts bytecode. And the client has that component embedded in the software. And what this comes from is the idea of having different implementations of EVM in a single Ethereum client implementation. So some time ago, it was even before the Ethereum launch, we had the prototype of EVM JIT, which is the software that actually translated EVM bytecode into LLVM and then to machine code. And the idea was to speed up the smart contracts execution this way. So we had C++ Ethereum client that actually was using two different virtual machines in this way. And I started designing, properly specifying the API for EVM to actually move the EVM itself a bit off the client. So it would be interesting, embedded somewhere inside, but I wanted to have some, let's say, stable API and separate these two components a bit. And what else can we do with that is actually like add more client implementations to the picture, where you have also the same API to reuse the VM implementations, and then you have some kind of combinations of different components, and yeah, it's getting fun. So EVMC started as by using C language to actually specify the API for that. So previously that was where the C letter came from, but we, in the process of renaming everything, we also renamed that a bit. So now it's officially called Ethereum Client VM Connector API. But still, C language is the way of defining what actually functions both sides have to implement. So why C? Because like C is probably the less favored language in this room, and why did we use C for that? So mostly because it happens that most of languages have some way of at least importing C libraries because they want to communicate with the operating system, they want existing implementations that exist for years, and don't want to, like, starting with implementing all of the libraries in new language if they design it so. And what else can I say about design of the EVMC? So it follows like polymorphic approach, which is it's tricky to spot on the first view because it's C and like there's no classes and interfaces, nothing like that. But you can design a class diagram of all the concepts, and mostly there are only like two classes. The first is the client, or the host, the piece of software that actually enables the VM to access the state, and the second class is the VM itself. And because of this, because of having the polymorphic design, you can also try to compose VMs in more sophisticated way. For example, have some kind of proxy VM that can actually inspect code and then decide which concrete implementation to use in this particular case. And all of that has two sides. So we have the client API defined there, and it was a bit coincidence, but it matches. So it was designed to support all this opcodes EVM that access and modify Ethereum state. But it happens it's quite direct, can be quite similar to the EI design from eWASM. So EI it's specifically the functions that are available to eWASM smart contracts. So you can directly map the C functions from EVMC to EI interface in eWASM. And on the other side, we have just VM API, and there's nothing more than the way to construct VM instance, destroy VM instance, and execute some message coming from the transactions. So all of that can be found on GitHub with this link. The main header function includes all the API needed with the documentation. You can also check out generated documentation, but warning, it's generated by Doxygen, which puts quite crappy web page out of that. And also I feel invited to the Gitter chat. Okay, so quick round of seeing what's actually how do we use it and where we can put it later on. So we have C++ client CPP Ethereum that recently has been officially renamed to Aleph, and it ships with C++ interpreter, and also you can use EVM-JIT to execute EVM contracts. EVM-JIT still supports all the changes up to Byzantium, but I think it's not properly maintained, so it passes all the tests, but I think it's not production ready. And what we added with the eWASM project it's here are the C++ eWASM engine, and uses exactly the same API. And there are two additional ideas, so like projects that hadn't been kicked off yet. One is probably to have separate high-performance interpreter implementation that it's not heavily coupled with Aleph codebase. And also Alex did some prototype of pure C implementation of EVM. But I just mentioned it for the full picture. And what is kind of work in progress, but is to add EVMC support to Geth. So the prototype of that is finished, and I currently have one node running on the mainnet with the Aleph interpreter. What is needed is to do some refactoring on the Go side to actually properly implement VM abstraction to allow have different VM implementations there. That's not ready, and mostly move the EVMC Go wrapper to different place to allow include that as a proper Go package. And when like the Go subproject is finished, I plan to use Python to actually add Python bindings for EVMC. I had a prototype long time ago, and it was as good as the PyEv app, what it's called back then, and it was able to reach the mainnet up to the DAO hard fork block when I think it's stacked. But I don't believe it's VM reason for that. And maybe if there's more interest in this project, we'll add Node.js bindings and Java bindings. If you have other languages you would prefer to see there, yeah, I'm open to actually discussion and do some work in this direction. Okay. So, questions?
So you kind of said it's in a prototype stage with Go Ethereum, but it actually works properly with the mainnet.
There's single glitch I haven't fixed yet. So there's this issue in the two. I mean, the Go bindings for C code. It's complicated because it requires like runtime assistance. There's a tool called CGO that actually generates code that will will help the calls to cross the go word and C word boundary when you have function calls. And then if definitely there's something wrong with that. It should also help you debugging issue with that with some runtime inspections. But in the end, it can happen. We have some very intense using of VM, especially with running state test in parallel. It can cause a crash of the Go, and I haven't figured out what the reason is for that. But it actually behaves quite okay on mainnet. So I checked all the blocks from the beginning, and it's still on the top of a mainnet.
Do you see any reason why this shouldn't be merged into Go Ethereum?
Yeah, I mean, unless we were not able to figure out the reason for the crash for, I don't know, 1 year, but yeah, I expect that to be merged sooner than later.
Yes, hi. So you mentioned that you could potentially run 2 VMs side by side in the same process or something like this. Like, what would be and choose the best one? What would be criteria for best VM that would require them to run side by side? And
it depends what you need, but it doesn't have to be any performance criteria. I mean, we have eWASM setup when you just select the VM based on the code you want to execute. So you can support EVM 1 bytecode and eWASM contracts on the same chain. So so actually in this case it works a bit differently. So mostly there's like in the chain the Hira is the first one, and it can answer with the rejection status code if the Hira discovers that the bytecode is actually EVM1 bytecode, and then you can just use the other VM to execute that. But that's what you would also like to have in case of JIT solutions. So it might be not worth it to JIT all the code. You can put some like strategy pattern on top of that and decide if you want to JIT the code or not based on some external input. So that's 2 cases I usually have in mind, but I don't think it's very extensively used at the moment. So.
Thank you, Pavel. So who wants to implement EVMC on their client? Is it status which is left? Everyone else has it. Before we jump into the JIT discussion, I just wanted to... We got internet during the break. So here's an example about the language support. You know, before the break we had these like handwritten things and big pieces of code. And it wasn't clear what is needed in a language to actually support eWASM. So there are 2 things usually in any kind of language. Well, 3 things. First of all, you need a language which can be compiled to WASM. And in any such language, there's going to be a way to import external symbols. So these are like the methods the eWASM VM would expose to the contracts. So this example here is the Rust framework we have, or Rust library. We just import these things which are exposed to the contract. And you can use it directly if you want it. That's what Casey has done in one of these examples. So he's just using them directly and manages memory on his own. But you don't need to do that. You probably would want to have a higher level API. So for example, this one, I would consider this like a middle level. So it wraps all these unsafe C-style functions into vectors and manages memory. But you probably would want to have, in any kind of language, an even higher level, where in, for example, this instance, it returns the current address of the contract. You would want to have it as like a big number or like an address type. So these are the things which need to be done in every single language which want to target eWASM. You will need to have a way to access the low-level functions, and you probably will need to have a framework to use them efficiently and easily without duplicating work. And we have mentioned that we have like 3 of these frameworks. We have one for AssemblyScript, which is nearing usability. It's going to be like super high level. And the second one is Rust, as you can see here. It's not fully finished, but it's not too much left to finish this. And obviously, the C one has received less resources because who wants to write contracts in C? I hope this was useful to get like an idea what is needed to make a language to support eWASM, but it's not too much effort to do that. Any questions on that? Cool. So let's jump into JITs with Casey.
Yeah, and just double checking, so about the file sizes of the WASM code. So the Rust example, which is incomplete, comes in at 290 lines. The AssemblyScript one, smaller at 250. But so the Rust is 789 bytes in the binary format, and the AssemblyScript one is 1011 bytes, so both about a kilobyte. The Rust one would probably be the same size when it's complete. Yeah, so if you ask me, the main advantage of WebAssembly is, the killer feature is that users will be able to deploy their own precompiles. It's cleaner, so EVM versus eWASM. There's the advantage that you get the language support, so you can write contracts in languages that compile to WebAssembly. But that and other ecosystem and tooling benefits, but generically speaking, the main ecosystem and tooling benefit from WebAssembly is the ability to use the JIT compilers that already exist for WebAssembly, so that you can execute contract code at native, like machine code speeds. If you can't do that and you just execute WebAssembly in an interpreter, then I don't think it would be worth the benefit of doing all the work to switch to WebAssembly. So to distinguish the engine types, there's an interpreter, then there's the compiled where you execute at native speed. For compiled, there's 2 ways to do it: ahead of time and just in time. So just to offer some rough benchmarks, so one benchmark we ran is the EC pairing precompile, the one that was added in Byzantium. The Rust version compiled to WebAssembly, run, and so we call it 3 times, which I think is below the gas limit, so you could do it in 1 block. In the interpreter, it takes 21 seconds. And a JIT engine, WAVM, it takes 100 milliseconds. So the difference between compiled speed and interpreted speed is enormous. So precompiles, it's called a precompile because it executes at native speed. And so it has its own, much lower gas cost than if you were running it in EVM. So when these features like, doing elliptic curve functions, they're too slow to do in EVM, so in order to be practical, we add precompiles. The problem with precompiles is they expand the size of the VM. It makes the VM, it has a lot of consensus critical code. And historically, precompiles are one of the big places where consensus bugs are found. So one example was the modXP gas calculation, which is very complex, very complex formula. I mean, it has to be complex because it's like an analytical formula for the algorithmic complexity of modular exponentiation. And they're very tough to test. It's easy to write some basic test cases, but nobody really volunteers to do thorough testing. These are the EIPs as they exist today. So, and it's not just, in some cases it's just lack of documentation. Nobody's updated the EIP with the test cases that we have. But even if you do that, you'll see that, there's a lot of potential test cases that that could be written, and if they're not written, then you have potential consensus vulnerabilities. Whereas if the precompiles were implemented in WebAssembly, then all the WebAssembly test cases that already exist, you guarantee that you have coverage over just the VM. So you don't need to generate test cases to cover all these edge cases for some other library that every client can pull in a different library. Let me back up a second. So people want more precompiles and they want them now. Those are supposed to be pitchforks. But client developers, or at least me, I don't want to add more precompiles because it's a huge burden on testing. If we were only going to add one, maybe, it'd be easier to just add one or two than integrating a WebAssembly engine. But if we're going to add a bunch of them, then I argue that it would be easier in the long run if they're all WebAssembly based. Because you get one universal gas rule, so you don't have a custom gas rule for each precompile, which are like these crazy formulas that are very hard to test. And clients could still do their own native implementation if, let's say it's the Python client, and you don't have a JIT WebAssembly engine, so the Python library might actually be faster than interpreting WebAssembly, just running an interpreter inside an interpreter. So you could use that to calculate the result, but the tricky part would be what is the gas cost? So I don't know, but there's a draft on this. So this might be a stepping stone to getting WebAssembly support on the main chain. See if people, any thoughts they have. By the way, if I start to ramble, please interrupt me and ask questions. Yep.
Can you explain a little bit about what is the injected metering and how does it solve the problem of the evaluation of the gas cost of the recompile?
Sure. So I mean, there's different ways to do it. I think is it branch based or?
The slides are there.
Why don't you go ahead?
No, you do. I have to mix it. Well, okay, doesn't matter. I can just go there. Yeah, these two slides.
Okay. Yeah, so it parses the WebAssembly and then counts the loops and branches and then injects use gas statements before those. So it's one universal gas rule. And so it's the same one that would be applied to every precompiled. But the challenge is with JITs. So we want to use JITs because it's the only way to let users deploy their own precompiles. So either we add 1 million precompiles or we use JIT execution. Or compiled execution.
Yeah, another question, super basic question. Sorry to interrupt you. On the slide, I think it was slide number 4, something when you were talking about the ways of running, yeah, that one, the different engine types. When you talk about AOT compilation, just to be very clear, that means taking WASM bytecode and ahead of time compiling it down to native bytecode for whatever platform the client is running on.
Yeah.
And so in practical terms, is this something clients would ever actually do? And they're doing what? They're doing that with contract code and they're storing it in a database or something like in x86 if you're running on x86?
Yeah, I guess you could imagine it. I mean, it sounds crazy to me, and Paul had a better way of explaining it, which is like you compile LLVM to WebAssembly, and then you so that outputs a .exe file, and then you save that exe file in a directory. So when somebody calls a contract, you run this exe file. So with an interpreter, the gas is charged at every step. With ahead of time, so the difference between AOT and JITs is that with the AOT, we can meter the compilation stage. With the JIT, we can't unless we built some kind of custom JIT where it was, we meter it. But then the actual execution phase is metered. So the vulnerability, the problem with JITs, the concern is the compile phase, which is not metered. So one of the EVM, eWASM developers, Greg Colvin, Wise, Gary Gandalf, was warning us about JIT engines and how they don't just do linear passes. We were optimistic that maybe WebAssembly JIT engines, because WebAssembly is designed to be validated in a linear pass, and so all the documentation say, oh yeah, it's just one linear pass and it's really fast to validate. We were hoping that it might be really fast to compile as well, but and we didn't know until a month or two ago when Guido Bronken, one of our fuzz tester, hooked up his fuzzer to V8 and found some pieces of code that are really slow to compile. So these are like 20 kilobyte pieces that take V8 2 seconds to compile. And so you can imagine if there were multiple calls to this in a block, well, it doesn't take that many before that 2 seconds per call that adds up. And we're not really sure what exactly the features are in the in the bytecode in the assembly that that the JIT doesn't like, but you can view them and you can scroll down and you can kind of see the patterns. Definitely nesting has a lot to do with it. So big nested loops probably are one of the issues. So there's 2 ways we can achieve native execution. One is with metered AOT. The problem with metered AOT is that then we can't use off-the-shelf JIT engines like in the browser, like Chrome, Firefox, or Node.js, or whatever. So yeah, so in case, you know, browser-based apps you win the war, then it would be nice if we could use off-the-shelf JIT engine. And it would also be nice even without the case, because it'd be easier for clients to just, you know, they could use V8 or Firefox's thing, or, you know, LLVM, WASM. So WASM is the one that we're using for planning to use with CPP, Ethereum, and here, well, with EVMC. So any client would be able to use WASM. Which, by the way, after Guido found these JIT bombs for V8, he said, what should I fuzz next? And I said, oh, we'll do fuzz WASM because we're going to use that next with CPP Ethereum. And he said, oh, well, yeah, I found a bunch of crash bugs in WASM, and then, yes, I also found, then was able to find the slow inputs, the JIT bombs. And I said, oh, well, that's interesting because EOS is about to launch their mainnet and they're using WASM. And so Guido had an exciting week of earning EOS bounties. So our 2 options are either try to do AOT or take the easy route, which is using JITs. If we want to use JITs, then there's 2 ways we can deal with the bombs. Either we can fix all the browsers, or we can try to detect the bombs. So detecting bombs, this is a slight twist on Paul's idea about compiling LLVM to WASM and then injecting metering in that WASM. So that way you can meter the compilation stage. So the slight twist on that is, rather than caching the compiled machine code and then running, you know, and then having clients run these EXEs, which would be harder than just using out-of-the-box, off-the-shelf JIT. Instead, we, I don't know, ban, you know, we reject any deployments of bombs. Or, I mean, it wouldn't have to be that way. Another option would be, if it detects a bomb, then run it in an interpreter instead, or something like this. Yeah, the bomb sniffer is one idea to still use off-the-shelf JITs. We have to explore it. I guess the next step is to actually compile LLVM to WebAssembly, see how big it is, see how fast it runs. Yeah, that's it.
How does doing a compilation stage better than doing an execution stage? Like, a bomb is a bomb. Like, it's going to slow things down and kind of.
Well, because
deployment stage.
Well, you don't let the bomb go off. You sniff for it and then you push it away before letting it into your house. You know.
So you cut off compilation at some point after a certain amount of gas has been spent. Or something.
Right. Yeah. So there'd be a threshold, you know, gas usage where once it exceeds that threshold, oh, it's a bomb. Then reject it.
So Casey, when you showed this diagram where different like interpretation and compilation of two types, you said that the JIT is much faster than interpret, but how much faster is it than AOT? Is it comparable?
Yeah, it's about the same.
But why won't you, like, what's the problem of just using AOT then? Like, why do you
if you use AOT, then you can't just use off-the-shelf JITs, like plug and play. I mean, there's a lot of development effort into writing your own custom AOT. Then also, you wouldn't be able to execute them natively in a browser.
So there are no off-the-shelf AOTs?
I don't know, maybe.
Because if they are comparable in terms of performance, and there are off-the-shelf AOT, why bother with JITs?
Well, I guess the browser would be my last argument. Is it'd be nice to have native capabilities inside the browser.
Okay, so the question I have is, why don't we just go back to something similar to a precompile? Because we can kind of vet.
Because if we go back to precompiles, then we have to add 1 million precompiles, and nobody wants to test all those.
Yeah, but I mean, at least we can vet them, right? That's the thing about it.
You can try to vet them, but
yeah, sure. But I mean, it's still more control. Like the thing with using a bomb sniffer is like you can only sniff. You can't predict. It's like whitelisting versus blacklisting, and you kind of want to. You know, you want to blacklist everything and only whitelist the things. And like, I'm worried about a bomb sniffer basically only detecting the things we know, right?
Yeah. Ultimately, the bomb sniffer, it wouldn't have to be like part of the consensus, protocol. It could just be a way, to safely run things in browsers. That way, if something is a bomb, then you can, deal with it or not deal with it, and then run everything else inside the browser.
Right. So you'd basically get exception. You could theoretically get exception like we have currently out of gas limits. Like we could throw exception. Like one node could say, well, it ran too long. Like it ran over like a second boundary for me. Therefore, I failed this transaction. And then like the consensus could pick up all these TX fails based on just it took too long.
Yeah, if the bomb sniffer was part of the consensus rules, but it wouldn't have to be.
Okay.
So you mentioned some performance numbers of these JIT versus non-JIT, but I'm curious, how much of the total time of a block execution is made up of bytecode execution versus state handling, network traffic, all these little things? I've looked at.
Well, most of it is state, reading and writing, because state I/O is the bottleneck. But state I/O is the bottleneck because people don't bother to, compile huge cryptographic libraries into EVM and then deploy them because they would cost too much gas.
Yeah. So how much of the problem is it? Like, do you expect?
So that's what I'm saying. It's not like JIT or AOT, or JIT eWASM is going to be a boon for scalability. It doesn't make every block run a lot faster. It only allows users to deploy their own precompiles. It's not going to, get you to 1,000 transactions per second, whatever.
I wanted to add to this answer is that if we had something which could run a non-state accessing code really fast, then we can actually ship some of the trade-offs. Because at the moment, if a state access is, let's say, in terms of thousands of gas, and adding numbers is like, whatever, 5 gas. So if you could shift the trade-off, it's like if it becomes like a million times cheaper to do arithmetics than accessing a state, then you can actually deploy some algorithms which trade the computation for the state access a bit more, as you said with the cryptographic stuff, or you can deploy more of this prover techniques and all of the stuff, so you will be able to do more of that. So it actually will be an improvement still, even though it doesn't address the current bottleneck, but it will be able to shift the trade-offs.
Good point. Any other questions, or should we?
More slides?
I don't have, no more slides.
How well characterized is the space of box? So in particular, both across JITs, I mean, you mentioned what V8, between versions, certainly these JITs will sometimes choose to, I don't know if de-optimize is the right word, but to say, like, to de-emphasize certain optimizations based on offscript usage, etc. What the boundaries are, like the amount of each recursion has to be in the example you showed, etc., etc. I won't belabor the examples here, but like, aside from beyond, sort of an elaboration, I guess, on the whitelist illusion.
So what was your question?
So how well characterized is the space of box?
Not well characterized at all. We just found these examples. We don't really. And Guido did have some hypotheses, but I mean, to really characterize, I mean, these examples are for V8, so to really be sure, you have to dig through the V8 source code and look at how its JIT works. Maybe, yeah, Paul.
V8 uses a DAG-based intermediate representation, and these loops have loops in the DAG, and that's why it's so slow, because the intermediate representation, there are maybe some linear pass JITs that only do one pass through the code, so that would be characterized, it would be perfect, but in this case, V8 is unusable for us because of these specific cases. But yes, I think we would have to look at the source code and what kind of IR they're using, what kind of techniques they're using. Maybe there's some register coloring algorithm that they're using that's quadratic or something like that. But yeah, very good points. If we can characterize the problems, we can pick and choose which ones we want to use. So very good points, very good question.
Thanks, and I guess a break for lunch.